Oh. All right. So, hi. How's it going? Oh my God, we only have 4 weeks left. 2 weeks before Thanksgiving, 2 weeks after, right? We only have 8 class meetings left. Isn't that crazy? So today, well, let's see, we were talking about series with positive terms. And so now I want to start talking about series where you can allow negative terms. We had all these tests that work for series of positive terms, but there's a series test 2 handout that's on the handouts page. And we're going to end up looking at that quite a bit. So if you're remote, you might want to pull it up for yourself. But I'll just share it for a few minutes. Okay, so, right, I kind of want to talk through this handout today and do some of the theory behind some of this stuff, and then there's examples. We'll definitely get to some of the examples before the end of class. But yeah, so the idea is like, all of a sudden now, if we allow terms, if we allowed negative terms in our series, so, I mean, one example you might think about is just the sum of sine of n, something like that, which kind of chaotically positive and negative. We don't really know. Like, I don't know if sine of 100 is positive or negative. It's something strange, right? Then that's kind of weird. And then it turns out that like we can't really use comparison tests, integral tests. But this is still true, right? Test for divergence is still always true. If the terms are not going to 0, it doesn't matter if the terms are positive or negative. If the terms aren't going to 0, the series has to diverge. And in fact, even though some of the other tests don't work, it turns out certain of these series are kind of nice, like alternating series. So this also says like you could have some chaotic kind of thing, but a lot of series we'll look at just alternate. You have plus minus, plus minus, plus minus. And so let me talk about this alternating series test and give you an example. So I'm just going to go to the board and do this. So, okay. I really hate when I leave myself on the screen. Yeah, so let's talk about alternating series and the alternating series test. So let's just do an example. Let's just start with an example. So what if I started with something like the following: 1 minus a quarter plus a ninth minus a 16th plus a 25th minus a 36th plus a 49th, and so on, right? You sort of see what I'm doing there. What am I doing? 1 over what? 1 over squares, right? So, okay, first off, how do we put this in summation notation? Well, we're going to have an n squared on the bottom. We're going to have a -1 to some power. Remember, that's how we encode alternating. There's -1 to some power right here. We're going to want to start at n equals 1 to make the denominators match, right? Like the first term is 1 over 1, the second term is 1 over 4, the third term is 1 over 9. And then we just have to make the power work. So it's tempting to just put n here for the power, because -1 to the n goes back and forth. But if we did -1 to the n, we would start with a negative, because we did -1 to the first, right? So really what you need here is n minus 1 or n plus 1. You just need to shift it by 1. So is that believable that that power will work? That this would give you, the first term would be -1 to the 0, so that give you a +1. Okay, so here's a series. Now I claim the series converges, and it sort of feels like a p-test series, but let me just but I think there's a simpler example, a simpler argument that this converges. So let's visualize this on the number line. Let's visualize adding and subtracting these terms on the number line. Because you'll start to see exactly, it's pretty easy to see that this converges, because let me just start, here, let's make a big number line. Between 0 and 1. Okay, so our first term is we add 1, right? So we add 1, and we land here. Then we subtract a quarter. It's probably more than a quarter, but I want a little bit exaggerated. So we subtract a quarter and we land here. Right, remember about the partial sums? We could think of this as like S1. This is like S2, right? S2 is SK is the sum from n equals 1 to k. So I'm just trying to visualize the partial sums on this picture, right? So S3, I'm going to add 1/9. Again, maybe exaggerated, but that's plus 1/9. And this is S3, right? Maybe I should have arrows here. There's an arrow going that way. There's an arrow going that way. There's an arrow going that way. Then I'm going to subtract a 16th. I'm not really trying to get minus a 16th. And we end up there, and that's S4. And now it's kind of hard to picture, but I might just kind of think about doing like adding and subtracting like this. That would be adding a 25th. And then subtracting a 36th. I'm just sort of like adding, I'm just going down to get out of the way of what I'm doing. Does that make sense? These vertical things don't mean anything mathematically. I'm just trying to get out of my own way. So this is plus 1 over 25, minus 1 over 36. And are you starting to believe this is going to converge? It's like trapped in a gravity well or something like that, right? It's going back and forth. It's bouncing back and forth. But in fact, maybe I should just do it like this. Sort of, it's a gravity well. And you are trapped. Yeah, so we're adding and subtracting. We're bouncing back less far than we went each time before, right? Bouncing back and forth. Each bounce less than the one before it. And the bounces are going to 0. Like these are getting smaller and smaller. The bounces are getting smaller and smaller, going to 0. Smaller and smaller. Going to 0. So this series converges. I think that's kind of the argument. That's the argument. And that's really what the alternating series test says. If you look at the handout, that's what this says. So this series converges. That's kind of, it just has to settle down and come to a stop. And that's what we know, right? We can see it here. And in general, so if we generalize this, we get the alternating series test. It's on the handout, but let me just write it out. So the alternating series test so we generalize argument above. Basically, what way this works is that, like it said, we're bouncing back and forth, each bounce less than the one before it, and the bounce is getting smaller and smaller going to 0. Bounce being just adding or subtracting. So given where do I start this? I guess I started counting at 1 for some reason. Something like this. So A1 minus A2 plus A3. So given something like that, if each term is smaller than the one before it, if A sub n plus 1 is less than A sub n, I said for all n, and I guess I'm assuming these are positive, then I'm putting the whole minus in here. So that's why I put it greater than 0. So maybe I should put if 1. I said for all n, but really it's just eventually. You could have stuff bounce back kind of weird for like the first 100 terms, and then eventually start going in smaller and smaller. So I'll actually say for all n sufficiently large. And 2, the terms are going to 0. What you're adding, the individual terms are going to 0. So, this is the bounce less each time. Or flat bounce less than the one before it. And this is the bounces getting smaller and smaller, going to 0. If both of these are true, then the series converges. That's what the alternating series test says. Okay. So this is kind of what how we wish series behaved in general. It's like you pretty much just need to check that the terms go to 0. And then you should see they're getting smaller. Back and forth. But in this case, most alternating series, in the sense that as long as the terms are going to 0 and getting smaller each time, most alternating series converge. As long as the terms are going to 0. Yeah. I can give you an example of something that's, I can give you examples that break each of these and don't converge. So let's try that. So non-examples. Breaking the first one's a little bit harder in terms of like, I stopped this share, didn't I? I haven't left the screen share on the whole time we've been here. Okay. I have to make a contrived example to break the first condition. But the second condition is really just like our test for divergence, right? If the terms aren't going to 0, then we're going to have a problem. The series just is never going to come to a stop. So sort of non-examples. So here's one. What if I had the sum of n plus 1 over 5n? Oh, I forgot my alternating. Minus 1 to the n minus 1 plus 5n. N equals 1 to infinity. Something like this. So, if we started plugging in numbers, we'd get, what, 2/5 minus 3/10 plus 4/15 minus 5/20 plus 6/25, is that right? I think I'm plugging in the numbers correctly. But check me. Seems about right. I always like to write out the first few terms of a series when I come across it, just to get a feel for what's happening with the terms, I think that's a good habit to build. But yeah, I think that's the bottoms are multiples of 5, the tops are just increasing by 1. Okay, so this feels like it might do the same thing as the previous one, right? But there's a problem here. So yeah, I mean, we can draw the same sort of picture, I think. Don't even need as big, well, 0 to 1/2, because we add 2/5, which is 0.4. Then we subtract 3/10, which is 0.3. And we add 4/15, which is, I don't know, what's 4/15? 0.26, something repeating. Anyway, so it's like we add 4/15 and then we subtract 5/20, which is 0.25. Right? So plus 2/5 minus 3/10, etc. But what happens as n gets large? What happens here as n gets large? It's going to 0? What if n's like 1,000,000? You get 1,000,000 in 1 over 5,000,000. N's like 1,000,000,000. You get 1,000,000,000 in 1 over 5,000,000,000. What's actually happening as n gets large to the terms? They're going to 1/5, right? It's like basically n plus 1 over 5n plus 1's negligible, n over 5n is 1/5. So then there's a problem, is that basically you're just going back and forth forever. It's supposed to be the same amount each time, but maybe you can draw it better yourself. So it's approximately plus 1/5 minus 1/5 plus 1/5 minus 1/5. So I think the terms are getting smaller each time. I mean, there's also a question of how do you justify that, but yeah, so condition 1, oh, that's not a good chalk. Condition 1 is satisfied, I think. Let's see, if you do like the n plus first term to the nth term, so the nth term is n plus 1 over 5n. Is it true that n plus 2 over 5, n plus 1 is less than that? Because this would be the next term, right? This is a sub n. This is a sub n plus 1. I mean, it's a question mark. You do have to think about it. You could think about the function x plus 1 over 5x and show that the derivative is negative if you wanted to show it was going down. I think that is true, but you could also do some, like, let's see, I can get rid of the 5s. It really, if I cross multiply, it becomes this question: is n plus 2 times n less than n plus 1 squared? And that's the same thing as n squared plus 2n less than n squared plus 2n plus 1. And there you can see it, right? You got the extra plus 1 over here. And so that's true if and only if 0 is less than 1, which is true. Okay, so that's kind of an argument you could give that, like, the first condition is satisfied. So the terms are getting smaller each time, but they're not going to 0. But 2, the limit as n goes to infinity of a sub n is the limit as n goes to infinity of n plus 1 over 5n. And remember, we talked about how to resolve these. You can just think about the plus 1 being negligible, but you can also do the multiply the top and bottom by 1 over n to force the infinities in the denominators. So you get 1 plus 1 over n over 5. Right, that's kind of the nice, that's how I like to resolve those kind of limits. Because now I've stuck the n in this denominator, so that goes to 0. So that equals 1/5, which is not 0. So the series has to diverge. I mean, that's kind of, that's really just a test for divergence, but also here it's like you can see it. You can see it in this bouncing back and forth forever, right? Bounces back and forth forever. The bounces, remember I was writing about the bounces on the before I erased this board. I said the bounces are going to 0. So in this case, they're not. So either way you look at this, this diverges. Okay, so you got to check both these conditions are satisfied. Does that make sense? Any questions about? You're just basically, so that was like saying that each bounce gets smaller than the one before it. Like it bounces back less far than the one before. So that's what's happening in this example. It's bouncing back less far than the one before it. That's what it means when the n plus first term is less than the nth term. It's like the n plus first term is the next term. Yeah, like, right, I guess what's happening, right. So somehow those are, it's still the lessons being maintained, but they're getting closer and closer together, and it's actually just going to 1/5. So even though it's decreasing, it's not decreasing to 0, it's decreasing to 1/5. And so you're basically adding and subtracting 1/5 over and over again. So it does satisfy that first condition, but it still diverges. Okay, so you get this oscillating divergence. To make the second condition, to make to violate the first condition but not the second, I have to do something a little more contrived, I think. Because I just erased it, but it almost feels like the second should almost imply the first. If the terms are going to 0 and they're all positive, then doesn't it feel like each term should be less than the one before it? For most formulas you write down, that would be true. So that's why I say I have to be a little bit contrived to give a non-example to this case. But you can do it. It's so here's an example that's a little bit hard to write in a formula, but I can write out term by term. So let's do this. Let's do 1/2 minus 1/4 plus 1/3 minus 1/9 plus 1/4 minus 1/16 plus 1/5 minus 1/25 plus 1/6 minus 1/36. You see, I'm kind of doing these in pairs, right? It's a little bit hard to parse this unless you do, like, you just think about them coming in pairs. So do you see what I'm doing each time? I'm doing just 1 over n minus 1 over n squared. So it is alternating. So I'm doing plus minus, plus minus, plus minus. It is, the terms are going to 0. Everything's getting smaller and smaller. It's like, you know, I'll have 1 over 1,000,000 minus 1 over 1,000,000 squared. Those are going to 0. So it is alternating. And the terms are going to 0. But I claim this has to diverge. And it has to diverge because it's basically the harmonic, it's basically the p equals 1 p-test series minus the p equals 2 p-test series, right? This really you could rearrange as the sum of 1 over n minus the sum of 1 over n squared. And this converges, but this diverges. This is infinite, this is finite. So could this whole thing be finite? No, because if it was finite, then they would all have to be finite, right? This would have to be finite, because this is finite. So yeah, this is that sort of, this converges, but this diverges. So the whole thing diverges. And you can see it's not true that each term is less than 1 before it, right? Like I go to 1/9, but then I actually get bigger. I go back to 1/4, which is bigger than 1/9. Then I get smaller, but then I get bigger. And I get smaller, but then I get bigger. So it breaks. We don't have a sub n plus 1 is less than a sub n here. Right. And in fact, if you tried to build this by bouncing, try to do my bouncing game, you would have something like a half minus a quarter plus a third minus a ninth plus a fourth minus a 16th plus a 16th minus a plus a fifth minus a 25th. So it would be, I mean, it's slowing down, but it's still the net each time. Like it's not trapped in the same gravity well, because the net difference each time is actually, in fact, you can see that each of these terms are actually positive. So you're actually adding a positive term series together. Okay. This is a terrible picture on the board, but hopefully. So not trapped in the gravity well. So like I said, that's a little bit contrived because I couldn't give that as one formula, but that's an example where the alternating series test breaks also. So that one you'll see less often. This one you really will see sometimes. So you do have to be careful to make sure the terms are going to 0. Okay. Questions about any of that? Oh, that clock is stopped. Is it 10 after 12? Okay. Okay, so that's the alternating series test. And then if you go to sort of the bottom half of this page of this, let's talk about this stuff for a few minutes. This is still a little abstract, but I'll give you some examples to hold on to. There's also some things you could compare, like, you know, we have these series like actually, let's look at another example. We looked at the alternating 1 over n squared series, but we could also look at the alternating harmonic series, like the alternating 1 over n series. Because we can talk about how there's like, you know, you have this series that alternates, but then you can sort of associate to it what's called the absolute version of the series, which is where you just make all the minuses into pluses. So let's try that. Let me stop this share. So again, if you're watching this later or remotely, just look at the bottom of the first page of this series test 2 handout. Okay, so yeah, let's talk about absolute and conditional convergence. Again, let's just talk about an example. Always the best place to start. So let's actually look at the alternating harmonic series. So by this, I just mean the series 1 minus a half plus a third minus a quarter plus a fifth minus a sixth plus a seventh and so on. Right? So you could draw the same picture, the bouncing. You could bounce forward 1, back a half, plus a third, back a quarter, plus a fifth, back a sixth, and so on. And it satisfies the conditions for the alternating series test. The terms are getting smaller each time, and they're going to 0. Satisfies the conditions for alternating series test. So it does converge. So that's interesting though, because the harmonic series didn't converge, right? And that's kind of weird. So this is a series, but then there's the sort of what's called the absolute version of the series. And it's absolute like absolute value. Turn all the minuses into pluses. See all my quotation marks and apostrophes, but hopefully that makes, or would these have apostrophes? Maybe they wouldn't. Turn all the minuses into pluses. I could have just written the word minus and plus probably. Turn all the minuses into pluses. So the absolute version of this series here is just, I mean, you can just do it 1 plus a half plus a third plus a quarter plus a fifth plus a sixth and so on. So that's the standard harmonic series, which we know diverges, right? This is not a finite sum. And I guess the thing that's interesting here is that this boxed thing in the handout, I think this is believable. Like, so if the sum of the absolute values, so that's another way to make the series into an all positive series is just write absolute values, right? If that converges, then so does the original series. Because like, I say it on the handout, intuitively the absolute version has a worse chance of converging. Because in the absolute version, you're just going to the right, you're bouncing to the right on the number line the whole time. So that's all, when we look at those kind of series, converging means slowing down to 0 fast enough, right? The terms are like the bounces are slowing down to 0 fast enough to come to a stop. But if you make some of them minus, then they're going to be bounced, some of the terms will be bouncing backwards. And so it's actually, and especially if you make them alternate like this, then you get trapped in the gravity well and it converges. So I guess what I'm saying is if the, so this is sort of a fact or a theorem. If the absolute version of a series converges, then so does the original series. That's kind of a big statement. That's a big. Let me give you an example that's less obvious, that makes it that I think will illustrate this. So here's a sort of interesting example. What if I do sine n over n squared? Sine n over n squared. Right, this is that thing where the sign is sort of chaotic. I can't tell you whether it's going to be positive or negative. as we jump around. It's sine of a million positive or negative, I have no idea. Sine of 10 positive or negative, I have no idea. I'd have to put it between a couple of multiples of pi. Let's see, right? Because pi is weird, it makes, you have to locate, you have to decide whether you're between an odd and an even multiple of pi or between an even and an odd multiple of pi to know whether the sign is negative or positive. So this is, you might think it's hard to determine whether or not this converges. Because sometimes it's positive, sometimes it's negative. But it's like, it's weird. But think about the absolute version. The absolute version is, well, I just put absolute values around the sign. Everything else is positive. The n squared is positive, right? Now this is a positive series. So we can start using all those other tests like comparison tests and stuff. What do we know about sine? The values of sine? What are they trapped between? -1 and 1. So the absolute value is going to be between 0 and 1. So in fact, this is less than 1 over n squared, that series, because sine of n is between 1 and -1. So the absolute value of sine is between 0 and 1. Right? And this is, that's a way to write converges. It's less than infinity. Right? So the absolute version converges. And that means the original series converges too. Space on the board. Okay. So it's kind of weird. Like this is a hard series to sort of think about term by term. Like it's just hard to like picture how the bounces are working. But they are, but it's somehow, because its absolute version converges, you don't have to worry. It's this series also converges. So even if you make all the negatives positive, the series still comes to a stop, which means if you make some of them negative back, then it's going to converge. Okay, fair. This material particularly dry. I feel like half the class is falling asleep. That's good. I was trying to do the bouncing, thinking that would be like, hey, look, guys, we're bouncing. This is bouncing all over the place, but it's bouncing to a stop. Okay. So this one up here, I just want to talk about a couple examples, because there's these the 3 bullet points at the bottom of page 1 in the handout, which is that there's 3 types of series now. You can either converge absolutely, converge conditionally, or diverge. So this example, the alternating harmonic series, well, so this example we just did converges absolutely. That's how we would say it. Because not only does it converge, but its absolute version converges. That's actually how we figured out it converged, because it's absolute version. So let me just write this down, because these are kind of avatars you can have in your head. Like, it's good to have a couple of like examples to illustrate the concepts. So, right. So we call the sum n equals 1 to infinity sine n over n squared absolutely convergent. It's almost like a stronger version of convergence. because its absolute version converges. And so it itself converges. Okay. But something like that alternating harmonic series, we call that conditionally convergent because it converges, but not, we didn't figure that out by looking at the absolute version because the absolute version diverged. We call this conditionally convergent. Because it converges, but its absolute version does not. Its absolute version. Okay, so that's like a weaker form of convergence. And then the third possibility is just that the series diverges, like something like that example we had before. Or I mean, any series that we had that diverged before is just divergent, right? It's not conditionally convergent. Any positive series, right? But something like the example we had. Diverges. Okay. So these are sort of the three. It's almost like instead of just convergent and divergent, we now have three possibilities, which is absolute convergent, conditionally convergent, or divergent. Okay. I think we should take a break for a few minutes. 12:24 on the clock here. So let's take a break for 5 minutes and then we'll come back and talk about the ratio test. Take a break. Pause the recording. All right. Let's talk about the ratio test, which is fun. People love the ratio test. You start wanting to hit every series of the ratio test because it feels very powerful. So yeah, let me show it on screen. But then I will actually do an example because it's sort of something to do with comparing each term of the series to the next term and actually taking the ratio, which isn't so unfamiliar to us. We did do that with geometric series where we saw what we multiplied to get from one term to the next, right? So let me do an example on the board. Okay, so I mean, here it's kind of like we saw some series like this last week, and I made some arguments that they converged, but like what if we look at ratio test? So let's look at an example like the sum of n over 3 to the n. And I could also make there be alternating and stuff too, but because it turns out this will work for alternating series. But let's just think about this. So this is, again, let's write some terms out. 1 over 3 plus 2 over 9 plus 3 over 27. It's 4/81. It's 5/243, and so on. You just take powers of 3. So you have all of this. The question is, does this converge or diverge? And an argument that we gave last week was, well, we could say n is less than 2 to the n. And so this whole thing is less than 2 to the n over 3 to the n, which is now geometric. So that is one argument. You could try to make an argument like that. But things do get more and more complicated. I gave you more complicated examples where it feels like it might be harder to make that argument. So let's just think about, let's think about what happens when n gets fairly large. So if we had something like the millionth term over 3, so 1,000,000 over 3 to the million. And then the next term is 1,000,001 over 3 to the 1,000,001. Like that, right? And what you might start to notice is that the numerator, the numerator is always increasing by 1, but sort of percentage-wise, it's increasing less and less, right? Here, 1 to 2 doubles, 2 to 3 is 50% increase, 3 to 4 is 33% increase, 4 to 5 is 25% increase. 1,000,000 to 1,000,001 is a very tiny increase as a percentage. But the bottom, I'm still multiplying by 3. So this is approximately like, it's not exactly, but it's approximately times 1/3. That's not really true for the small terms of the series, right? Going from 1/3 to 2/9 is actually multiplying by 2/3, so that's very much not multiplying by 1/3. So it's not true for the small terms, but for large terms, for n large, going from a sub n to a sub n plus 1 is approximately the same as multiplying, or maybe I should say it this way, just easier way to say it is a sub n plus 1 is approximately 1/3 times a sub n. Right. But then that's just like a geometric series with r equals 1/3, i.e., the series starts to behave more and more like a geometric series. As n increases, as n gets larger. And because r is the multiplying factor, right? It's the common ratio. It's what you multiply to get from one term to the next. And so here r equals 1/3. So the series converges. Right? It's basically like in the first million terms of the series don't matter in terms of convergence or divergence. And then from then on, it's just like multiplying by 1/3 basically. And so that's an argument that the series converges. I mean, you could be a little more, I could be a little more rigorous about it probably. But the fact is this is basically what the ratio test is going to tell us. So this is sort of made abstract. This idea is made abstract in the ratio test. Or is abstracted into the ratio test or something. Abstracted into the ratio test. So what that says is, given a series, And now this could be positive, negative, whatever. Like these don't have to, you know, this could be alternating. It could have some weird chaotic mumbo jumbo going on. Consider or calculate, given a series like this, calculate the limit of the n plus first term over the nth term. And actually do absolute values on it just turns out, because if it turns out it's chaotic or alternating or something, you basically were considering the absolute version of the series in some ways. And I think, sorry, they call it L. So calculate L. So here, by the way, we could have rewritten, I could rearrange and write this as a sub n plus 1 over a sub n is approximately 1/3. And the limit really will go to 1/3 as it gets large, but we'll see that in a second. So that's basically what you're doing, is you're taking the limit, the ratio of consecutive terms. Okay. And then the test says if 3 possibilities. L is less than 1, L equals 1, or sorry, L greater than 1, and L equals 1. So if L is less than 1, then the series converges absolutely. You can see it on the screen where I'm going with this. Series converges absolutely. And it's basically because we're saying like we got a number less than 1, like here we got 1/3. So it's like a geometric series with R less than 1. But if L is greater than 1, then it's like a geometric series with R greater than 1. What do those series do? Geometric R greater than 1. Diverge, right? And the series diverges. But if L equals 1, then that tells us nothing. This is one of those no information. Remember like the second derivative test, if you want to know if something's a max or a min. Second derivative is positive. It's a minimum. If second derivative is negative, it's a maximum. If second derivative is 0, you get no information. It's a similar thing here. It just doesn't, basically it's like this wasn't the right test. And I'll give you a couple examples of that too. But okay, so yeah, let's actually do this as an example, and then let me show you why the L equals 1 case is no information. So I gave that argument sort of like not completely rigorous argument up at the top, informal argument at the top, but let's just hit it with the ratio test. So example, let's just do this example again. N over 3 to the n. So here a sub n is n over 3 to the n. A sub n plus 1, that's the next term. You just replace n with n plus 1 everywhere, right? Does this make sense? This is something students sometimes have trouble with. It's just like, if this was the 7th term, was 7 over 3 to the 7th, then the 8th term would be 8 over 3 to the 8th. You just replace n with n plus 1 everywhere. And then, so what is a sub n plus 1 over a sub n? Well, on top, we want this thing. I guess I should put absolute values, although it doesn't really matter here because everything's positive. On the bottom, I want this thing. Right, now it's like fraction over fraction. What do we do when we divide by a fraction? Flip it up, flip the bottom up. So this is like n plus 1 over 3 to the n plus 1 times 3 to the n over n. And I claim there's some simplification here. I have the number of 3's on the bottom compared to the number of 3's on top now. Yeah. Yeah. There's one more 3 on the bottom than on top. This is like 3 to the 10th, and that's 2 to the 11th. So the 3 to the n cancels, and you're just left with the 3 on the bottom, right? So kind of like you can cancel this and cancel that. So that's n plus 1 over 3n. And if I want to be able to take the limit as n goes to infinity, I can do the same divide by n on the top and bottom trick, or multiply by 1 over n. Force these in the denominators. So that's 1 plus 1 over n over 3, which goes to 1/3 as n goes to infinity. So that's the L, right? I didn't actually write the limit, but that's the L, like L equals 1/3. Which is exactly kind of what we set up there in the example, is like when I looked at it informally. L equals 1/3. 1/3 is less than 1 last time I checked, so the series converges. Converges absolutely, although here that also doesn't mean anything because the terms are already positive. Okay, that's how the ratio test works. I'll tell you, like, all the p-series tests give L equals 1, which is why it's not predictive. If you try any of the p-series, if you do that, then, which this sometimes converges and sometimes diverges, right, depending on the value of p. But if you do, so a sub n is 1 over n to the p, a sub n plus 1 is 1 over n plus 1 to the p. And so the ratio limit as n goes to infinity of this, well, now if we do the top over the bottom, I think we get this divided by this. This is on the bottom, so it will flip up on top. And so we'll get n to the p over n plus 1 to the p. You just do some of it, if you just actually write that out, you'll get that. But that is n over n plus 1 all to the p power. The inside goes to 1. N over n plus 1 goes to 1. So this equals 1. So L equals 1. So that's the thing. It's like, that's just not the right test because it just always, sometimes it converges, sometimes it diverges. This is why L equals 1 tells you nothing. So L equals 1 for all p. But some of these series converge and some diverge. That's what sort of illustrates L equals 1. So L equals 1 is non-predictive. You know. Okay. That's fair. Makes sense what I'm saying. Yeah, so that's why it's like tells us nothing. And there are, so there's going to be this thing where we start to try to figure out what series test to use for which series, just like you, if you're faced with an integral, it's like, which integral technique do you use? And I will say that if you see exponentials, a lot of times the ratio test is going to be helpful. But if you see, and actually factorials are sort of interesting. So here's a bunch. So if I share screen for a second. Yeah, so after the ratio test, there's a bunch of examples to try. And now it says determine whether each one converges absolutely, conditionally, or not at all, basically. Wait, before we do that, are there any questions about ratio test? I mean, teaching into lunchtime is hard. People are thinking about lunch, or they had lunch and they're sleepy from that. Yeah, so every one of these series we can sort of try to attack with different tests we have. You can just start to put crazier and crazier expressions in, like number 9, n factorial squared over 2n factorial. That's a fun one. Number 1 we've basically done. That's the alternating harmonic series, right? So we said that converges conditionally because it's converges, it's alternating and has that nice alternating behavior. But if we made it absolute value, if we turn all the minuses to pluses, we get the harmonic series which diverges. Let's do number 3. Actually, take a couple minutes. I claim you want to use the ratio test on number 3. So we don't have that much time left, so just at your seats, write down number 3. Try to identify the a sub n and the a sub n plus 1. Try to write down what those mean. Does everybody know what n factorial means? Do you remember? N factorial means you multiply the numbers 1 through n. So 7 factorial means 1 times 2 times 3 times 4 times 5 times 6 times 7. Because you're going to want to think about specific numbers maybe. So try the ratio test on. I claim the ratio test works on number 3. So take a few minutes at your seats, try to do it. Try to write down a sub n. Try to write down a sub n plus 1. Try to start writing down the ratio and simplifying. See what happens. Because I would say this is one that's a little like not obvious, like whether the top or bottom grows faster, 2 to the n or n factorial. So you might not know if the terms are going to 0 or not. So you have to think about this a little bit. So it turns out the ratio test is very powerful. And we'll tell you what's going on here. Okay. So write out, talk to your neighbors, compare notes. Number 3. Here, I'll be, let me see how ridiculous I can be. Do you know which one I want you to do now? So yeah, try the ratio test like we did in that example up there. Write down the n plus first term and see if you compare to your neighbors and see if you have the same thing. Check in. What is a sub n plus 1? Should I write? Yeah, and so actually you got to be a little careful here that it's like that. Because n plus 1 is the thing that's being factorial, not n factorial plus 1 or n plus 1 factorial. Right. So I like to put the parentheses around the n plus 1. Another minute or two. Cancellation is the interesting part here. How this cancels. If you're not sure, you might think about a specific n. Try like n equals 6. Try like the 7th term over the 6th term and see how they actually cancel. I really think that's, if you're not sure, try like a specific n value and see what happens. What does this cancel to? Yeah, if you want to be super duper pedantic about this, I could really write out exactly what the top means. That's the top, and the bottom right? Math, you can always write it out more explicitly. You can always try examples. And so, haven't you just said what? All the 6 of the 2's cancel. So there's 1, 2 left there. And then what cancels here? Yeah, 1, 2, 3, 4, 5, 6 all cancels. 1, 2, 3, 4, 5, 6 all cancels. And so you're just left with 2 7ths, right? So this does cancel nicely. So did anybody sort of see what happens in general? So an plus 1 over a sub n. It's 2 to the n plus 1 over n plus 1 factorial. I'm just going to skip the step where I write it as a big fraction and flip it over and just goes directly to the right. That's divide and flip over. And so I guess the question is, how does like n factorial and n plus 1, like how do these cancel? What's left? N plus 1 is what's left, right? Because this is 1 through n. And this is also 1 through n, but also times n plus 1. So the 1 through n's cancel on both. In general, you can think of something like n plus 1 factorial over n factorial is just n plus 1, because that's exactly how you get from n factorial to n plus 1 factorial. You multiply by n plus 1. So this, and you said all the 2's cancel except for one of the 2's. It's almost like you can cancel the n factorial and the exclamation point. And you just get 2 over n plus 1. So what's L? Just to finish this off, what happens as n gets large now? Yeah, so L is 0. L is the limit as n goes to infinity of this ratio, which here is the limit as n goes to infinity of 2 over n plus 1, which is 0. L is 0. What that says is that's actually like, it's almost like a geometric series, but with R smaller than any possible, like R smaller than 1/1,000,000, like R. What actually is happening is n factorial actually grows really, really fast. It's a lot faster than 2 to the n. That's actually one of the things that grows faster than exponentials is factorials. Factorials grow super fast. And so at the bottom, it's basically here that the bottom is growing really fast. The top is growing less fast. So the ratio is going to 0 very rapidly. So the series has to converge. So if you get 0 out of your ratio test, it's really just like, wow, that really converges. So this series converges. It's like even faster than any sort of geometric series. Okay. So that's kind of a nice general fact to keep in mind, is sort of like the way factorials cancel. There's some ones that get interesting in here. Like you can kind of make up some really pretty nasty, like number 10 is one of my personal favorites, n factorial over n to the n. Like the answer is surprising. What the ratio test spits out is surprising, but it does spit out a number that's non-zero. Number 9 is also kind of fun. We'll do some of these in class. We'll start on Wednesday with some group work, doing some of these, just trying some of these out. Just trying to talk them through, sort of like we did last week. Then we'll come together and actually, yeah, like check our work on, check our answers on some of these. Then we'll move on to power series, which even works. Okay. I think we're a little bit early, but let's call it. It's 1 o'clock. Let's call it early. All right. I have office hours this afternoon. I did post the problem set yesterday morning. There will be problem sets next couple weeks. I'm working on your tests. Let me stop the recording.